Do you hear me now? Ah, yes. Okay, good. So we'll begin here on the last section of the course. We had electricity, magnetism. Those things were related eventually to light. And we did optics, where we treated light both as rays and also its wave nature when you have diffraction and other phenomena that depend on the fact that light is a wave. Now we're coming to a new part of the course, which in the book it's called Modern Physics. Well, it's more than 100 years old when this started, so I'm not so sure that it should be so strange. And the truth of the matter is, you've had a lot of this material in high school, and in your chemistry courses, if you've taken any physics at all, this material is already covered. And we use already the words here, atoms, molecules, and such. Truth of the matter is, 100 years ago, would not have been obvious. There were people 100 years ago that did not believe there were such things as atoms because you couldn't see them. And they said anything you can't see or really observe directly should not be part of science, which is a philosophical point of view. That's pretty fair. But it took a long time for the idea of atoms to be accepted, but the reasoning and the evidence for it and for them was indirect, clearly, because we did not see atoms really very clearly until about maybe 20 years ago, when some tools were invented which allowed us to directly visualize it. So by then, pretty much everybody agreed, although by about 1920, the opposition to those ideas was pretty well silenced. But one thing that I did want to point out to you that strikes me, many books say quantum effects have to do with atoms and things on a small scale. That really isn't quite fair, I would say, because the fact is that most of the things we do on our scale, a macroscopic scale, human scale, are derived from quantum mechanics. Things like the fact the fact that things have color is really a quantum mechanical effect. We understand it we've only understood it with quantum mechanics. We understand things like the hardness of things, why some things are hard, some things are soft, some things are flexible, some things are brittle. That comes out of quantum mechanics. That's a macroscopic effect. We'll see here such things as how much heat a thing absorbs in order to raise its temperature, known as a specific heat, something you will have touched on in 8A, I think. That idea, how much heat a thing absorbs, is a macroscopic effect, and it's very much influenced by quantum mechanical effects. But they start out, in a sense, they start out with atoms and molecules, but we have very real manifestations of them on our scale. So it shouldn't be thought that this only has to do with obscure atoms and the electrons is jumping between levels of a hydrogen atom. No, it's much, much bigger than that, if you look at it, I think, correctly. Now, the outline of the course of this particular section in chapter 34, which is particles and waves, we start out, see, originally with the original idea of quantum mechanics came out of a very macroscopic phenomenon. So we can get that to work. Well, let's hope it's right. Sorry. Okay, let's go back to this. Yeah, we start out with what's called black body radiation, which I'll explain here today. Then, soon after that phenomenon was sort of measured and theoretically predicted, came another effect called the photoelectric effect. In this phenomenon, in the black body radiation, we got the idea that the energy of things was not smooth and continuous, but rather discontinuous, which is the reason for that particular music that I was playing for you was Stravinsky's Firebird, which is Stravinsky in those years, he was writing this music around 1910, about the time of these discoveries, and his music was very jumpy, very irregular, very chaotic. In fact, the famous story is that in 1913 he put on a piece called "The Rites of Spring," R-I-T-E-S, the rites. It was a primitive dance, a fertility dance, and a young girl dances herself to death. Bum 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 ba da ba 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 da. Crazy, and it caused such an outrage in Paris when it was performed that Stravinsky had to hide because they were going to kill him. I mean, they were throwing eggs and tomatoes and stuff, and he was just vilified. A few years later, they accepted it. But the Firebird is a little bit like that, if you noticed it. So the idea that things were irregular and jumpy was the idea that is behind quantum mechanics, that things have energy levels. This is where the idea of energy levels comes from. And it started out with the black body radiation, which I'll try to explain to you. Then, if you don't already know, which you may, then came another important phenomenon wherein light shined on materials, seemed to eject electrons from that material, called the photoelectric effect, which was inexplicable by the theories of the time and what you already know. From what we already know about light and matter, this phenomenon should not have occurred the way it was observed to occur. It contradicted what we already know. So we're going to need some new ideas to understand this effect. And then we come up with the idea that the energy of a wave depends on its frequency. In all waves seem to have this phenomenon. Now, this is a very new idea that comes out of these two observations. Then the real shocker, well, that was shock enough, actually, but a big shock is that material particles also have a wave-like character. So even in addition to their particle-like character, they also seem to have wave-like character. And that's an effect that to this day puzzles people, just how it could be. And we'll sort of justify it and sort of live with it because it explains a lot of things. So this is the so-called wave-particle duality, that particles seem to act like waves sometimes, and waves seem to act like particles sometimes. And sometimes they act like particles because that's the way we grew up to know them. So it's a funny business that we're getting into, but we have to learn to live with it because that's the way the world seems to be. But the story starts with the black body radiation. And again, I point out to you the marvel of this is that the physicists tend to start with very simple stories because it's hard to explain complicated things. So we start out with very simple things, like I'm going to start out with a box. Just a simple box, which is white on the inside and so on. And the question is, if you heat this box up, what kind of radiation will come out of it? Now, you think that would be a very simple question, but the answer that we finally came up with was very complicated. And it required whole new ideas. So the basic question that I put up there is, why do warm things glow? Well, you know that, for example, the old-fashioned incandescent light bulb, you put in electricity, it gets hot, and the hotter you make it, the brighter it glows, and even its color changes from sort of reddish to whiter, and so on. Okay, so why does that happen? That's a fair question, right? That's physics. Why do things happen, or how do they happen? Okay, so we could start to answer that on the basis of what we've already learned, but combining it with the ideas of the kinetic theory of heat, because what we're saying, I heat the box up. So I have a box. Let me make a square or round, it doesn't matter, with a little hole in it, and I heat it up to a certain temperature. Okay, so do you recall what the meaning of temperature is? Let me move on perhaps to that. Well, okay, let's talk generally first. Temperature has to do with the motion of particles. As a thing heats up, the particles move faster and faster, they jiggle more. In a gas, they just pick up speed. Now, I had a nice applet that showed that, wherein I could have a chamber, I raise a temperature, and it actually counted this or measured the speed of the particles in the gas. And you could see that as the it's very squeaky chalk, the energy, or the half mv squared of these particles, as you raise the temperature, would sort of go up like that. So the average, but that's an average, you see. So in fact, what's happening is that you have the molecules bouncing off each other, and they have all kinds of speeds. Some of them actually have zero speed at a moment, and some of them are going very fast, but there's a whole distribution. Are you familiar with these ideas? This is not. Okay. Well, that's very good. And all that's really happening is that on the average, speed picks up as you raise the temperature. And that alone was a great idea. That was an idea that came out around 1850 and 60, that heat was motion, basically motion. And the higher the temperature, the greater the motion. Okay, so from that idea, you can sort of get an idea of why a body might radiate, because we said, according to our ideas, that when charges accelerate, they radiate. Radiation. So you can imagine an atom coming along, it bumps into something, it bounces off, so it's accelerating. Both of them are accelerating. And you can imagine the electrons being jiggled, jostled, changing their motion, and so they radiate. So you would think that as long as you have motion and particles banging off each other, you will get some radiation coming out. So that's why warm things, temperature, makes the thing glow. And you would think that as you heat the thing up, it gets faster and faster, more and more rapid collisions, and more, in fact, the frequency of the radiation should come out because they're bumping against each other more often. So you would expect something like that. So there's a very nice qualitative explanation of why things emit electromagnetic radiation. Truth of the matter is, anything that has any temperature at all is emitting some radiation. You and I, for example, of course, are emitting radiation. You know, you can do these night vision things, and you can see a person glowing because his radiation's coming out of it. You're actually like a light bulb. And then you get the extreme cases like the stars, like the sun is at 5,000 Kelvin. So it's radiating very high frequency radiation, visible light. We are radiating, as we'll see, infrared radiation at a much longer wavelength, much lower frequency radiation, invisible to our eyes, but a snooperscope or a night vision thing can see that radiation that we and the Earth are radiating. Everything at 300 Kelvin, which is where we're at, is radiating at a certain amount, and we're roughly at the temperature of the Earth. So the idea of this review is probably too much, but the main idea is that we can actually make a connection between the gas law, PV equals nRT, you remember way back when, this one? PV, actually, if you do a molecular analysis of what is pressure, turns out that it's the average kinetic energy. And if you multiply P times V, you get something which is proportional to the average kinetic energy. But it's also proportional to T. So that justifies my comment that the kinetic energy on the average is, total kinetic energy average is proportional to the temperature. So that's your connection between the kinetics of something, the motion, and temperature. It's a direct connection by the law, the kinetic theory. In fact, we even use per atom, per molecule, or per unit of mass, the kinetic energy in one dimension, let's say in the x direction, is proportional to the temperature by this constant, which will be showing up a lot, called the Boltzmann constant. It's the Boltzmann constant is the gas constant that you learned about in gas. It's the number of moles times a so-called gas constant. If you divide by the number of atoms, you get what's called the Boltzmann constant, which is sort of the gas constant per molecule or per atom. And very wonderfully, the kinetic energy is directly proportional to this Boltzmann constant over 2 for each, for each direction. So in 3 dimensions, if you have three ways of moving, you get 3 of these. You get 3 halves kT. I'll keep calling it kT because it's K Boltzmann T for each degree of freedom. So at any given temperature, you have a certain amount of kinetic energy in each direction on the average. Again, it's a distribution. Then I would have been pleased to show you this in this applet. Maybe you can look it up on your own computers. So we'll just go on. But this is interesting because so we also learned in thermodynamics and other places that if you have 2 things at different temperatures, they will tend to come to the same temperature if they're in contact. That's sometimes called the 0th law of thermodynamics. Just 2 things, if the temperature is different, over a long time they will come to the same temperature. Now, temperature, we just said, is energy, so that's a very important thing. Let me write that down forever and ever. Temperature is related to kinetic energy. So if you have a bunch of things and you put them in contact, they'll come to the same temperature, they'll come to the same kinetic energy, which is a half mv squared on the average, some kind of average. So this is kind of a little fun exercise here where I have different kinds of balls. This is a heavy one, and this is a styrofoam that's even lighter. Do I have a ping pong ball here? Yeah, that's good. Okay, so so I have different masses here. So if I jiggle these together, sort of like temperature, they should have the same kinetic energy. But if one has lower mass, it's going to have a higher speed. So it's more likely to pop out because it's moving faster. So let's just see if that's true. This is known as equal partition. I'm giving them all the same energy, sharing the energy equally among them all, but that doesn't mean their speeds are the same. If their masses are different, by that rule there, to make the energy the same, the speed would have to be higher. So, okay, so what came out? Okay, the lighter ones. Okay, thank you. Which one is that? Styrofoam? Yeah, I guess that's lighter than even the ping pong ball. For what it? Oh, someone hit this one hard. Okay, I don't know which is lighter, but the light ones come out fast. The heavy ones don't. So that's the idea of equipartition, and it's sort of a very deep idea, in sort of obvious from this kind of consideration, that all particles should pick up the same energy. So that's that little demo there, the balls. And here's the example of a black body, namely it's a box. But you see, light will get into this box through that hole, but the white light, because it rattles, it can't get out so easily, it rattles around and it comes into equilibrium with the box. In equilibrium with the box, this box is at a pretty low temperature, like our temperature, 300 Kelvin roughly. And And so this box, once that light gets in there and can't get out, it equilibrates to the temperature that we're at, 300 Kelvin roughly. And at 300 Kelvin, it's emitting radiation. There is radiation coming out that hole, but it's the invisible radiation, the same kind of radiation that's coming out of you and me. So it's invisible. So that's the idea of a black box. Now, or a black body. If you heat the thing up, if I heated it high enough, it would start to glow. This is like, ask any blacksmith that you know. How many blacksmiths do you know? When they heat up the horseshoe, it starts to glow. Or if you've ever worked in a steel mill, which I haven't myself, but it would be an example. Now, here's the thing that I wish I had my demo teed up to show you better, what this is doing. So this is what happens if you really heat a thing up very, very hot. Like if you went up to 3,000 Kelvin, which is hotter than most lamps that we have, like incandescent lamps. But you see, you get this kind of radiation. This is the spectrum here. And you'll notice that there is a peak in the spectrum. This is very important. There's a peak in the spectrum of where the most light comes out, what the frequency which the light comes out. If you raise the temperature, not surprisingly, the peak shifts. Everything goes up. So the area under this curve goes up. And the peak shifts toward the shorter wavelengths. And if you heat it even more to 5,000, this is more or less the temperature, getting close to the temperature of the surface of the sun. You get that the frequency range peaks right in the middle of our visible range. The reason we see in this range, presumed by evolutionary thinking, is that this is the light that surrounds us coming from the sun, and so our visual sensors have developed to be able to see this spectrum of light. That's the visible spectrum, and this is roughly the spectrum coming out of the sun. So now this kind of measurement was made around 1860, 1870. After the idea of the wave theory of light, Maxwell's great 1860 discovery, people started making gratings to look at the light coming out of things and examining all the different wavelengths. They say, so all of a sudden there's all kinds of possible visible or invisible light. Let's go measure its wavelength. So they started measuring everything they could. And what a simple thing like this is just heat up a box and see what radiation comes out, because that's equilibrium radiation. See, it's not a fancy system. It's simple, and it should be able to analyze it. And so what that curve is the light coming out of this hole if you heat the whole box up to, say, 3,000 Kelvin. And you put that light through a grating, spread out the spectrum, and you measure the intensity at every wavelength. How much energy is coming out at every wavelength. That's what that curve is. And it looks pretty sensible. And in fact, they even got a law here for the wavelength at which the peak occurs as a function of temperature. And it came out very simple. The lambda at the peak, that's called we call it lambda max. It means not the highest frequency you can measure, but the wavelength at which the emission is greatest. Times the temperature is a constant. So which says that, I like much better to put it this way, that as the temperature goes up, because the wavelength is inverse as the frequency, as you know, many times we've said this. So, see, unfortunately, when you do a diffraction grating, as you will in class this week, I think, you measure the wavelength, right? Because you're using the rule n lambda. What is with this chalk? N lambda is d sine theta. So what they did, they would have a grating. They'd shine the black box, the black body into this. They'd get the spectrum. And they'd measure the intensity at various angles, and from this they would deduce the wavelength of the light. And when they plot that against the wavelength of the maximum, against temperature, they got a constant. Now, unfortunately, what they didn't do was say the wavelength times the frequency is equal to the velocity of light, so that the wavelength is equal to c over frequency. So what they could have put in was, instead of lambda max, they could have been c over maybe some maximum frequency times the temperature is equal to a constant. And what you would get from that is that you get f, let me put f max on the other side, and get c t over some constant. Now that, turns out, is where the physics is. That turns out where the physics is, because now we connect the fact that temperature is energy. This is saying that somehow frequency is related to energy. That's the breakthrough idea. So that you have here frequency is related to temperature, which is related to energy. So let me be so bold as to say that energy is some constant times frequency. If I had said that 110 years ago, I would have won a Nobel Prize. This is what Einstein said. And he won a Nobel Prize. That's what he won the Nobel Prize for, actually. That idea. Because that explains the photoelectric effect and a lot of other things. So, but that's the key idea. And it jumps out at you from this if you just look at it the right way. Again, what I like to say, it's a very simple experiment, and a very simple connection, but it's profound, it turns out. So that's why I like to do it in this way, say that the energy is proportional to the maximum energy is proportional to the frequency or the temperature. Now, so here's what they had been able to learn about the black body radiation. That, first of all, there is this idea that as you raise the temperature, the curve gets larger and shifts to longer wavelengths. I should really do it. Let's be smarter. Let's do it as a function of frequency. So as the temperature goes up, the frequency of the peak goes up, and the whole curve gets larger. The area under the curve is the total radiation goes as the fourth power of the temperature, the area. And the peak, the frequency at the maximum, is proportional to the temperature. So those are the two laws. This one is known as the Stefan-Boltzmann law. And this one, the way they usually write it this way, it's called the Wien law. Of course, I guess he was the first one that noticed it or else explained it or something. But in any case, it goes under that name. I don't know that anybody really has a name for that. We'll call it the Jordan law. Okay. The fact is that neither of those results could really be explained by classical theory as we know it. The point is that, see, the argument that gave trouble was this very argument about everybody having the same energy, because what you could say, what Planck thought about was, let me imagine a very simple model of the walls of this box. It's a bunch of dipoles, atoms. He didn't know what atoms were exactly, but this was 1898, so they really didn't know quite what atoms were. But he imagined that there must be something, and we know that the boxes are radiating, so imagine a dipole and it's radiating. But if you have all these dipoles and you're shaking the box, every dipole should have the same energy. According to an argument like this, they're at a certain temperature. They should have the same energy. They should all be radiating. That means that if I go out in frequency, or in wavelength here, the classical argument would be that no matter how far out in energy I go, or how far out in wavelength or let's say frequency, the higher and higher frequency, I should get some energy everywhere. In fact, I should have the same energy everywhere. According to this, everybody's in thermal equilibrium, so I should maybe have constant energy all the way out forever and ever. But you might say, there are various other arguments that, in fact, it's even worse than this. There are more ways of vibrating. If you have an object, if you have a long wavelength, there are very few ways you can get a long wavelength into an object, but short wavelength, you can get more of them in. So actually, and technically, at any given frequency, there are more of these high-frequency guys, so the energy should actually be going up and up and up as you go higher and higher in frequency, because every possible mode is in thermal equilibrium. They have the same energy. So what the theory would say, that as you go up in frequency, every mode, every possible vibration of that box should get some energy. The total energy should go crazy. It should keep going up and up and up to infinity, which doesn't happen, because that would say that you need an infinite amount of energy in a box. It just doesn't work. In fact, what happens, as we saw, it turns over at a certain frequency, and the amount of energy goes down. So that as you get higher and higher in frequency, these modes do not get excited and are not available. Well, I have 15 minutes. I'm going to hang on to this because this is not explained in the book. I'm going to try to finish explaining this because it's not explained in the book, and most of your introductory texts don't bother explaining it because it's all mathematical in detail. But the actual physical feeling is not that hard. So let's hear it once in your life, if you don't mind. The point that what you need then somehow is you have to get rid of all these high-frequency modes up here. They somehow do not get energy, despite the fact that they're in thermal equilibrium. See, this is the argument that long waves, there are only few of them can fit in a box. If you have short waves, a lot of them can figure. So actually, all these modes should get some energy by the shaking of the box, and you should have a tremendous amount of energy. As I think it was Richard Feynman in his book, he says if this classical argument were true, you could look into a fireplace and gamma rays and X-rays would come out, because there's no reason for them not to come out. Every mode that's possible in there should be excited. So you should have X-rays coming out of your light bulbs. It doesn't happen. So, but what it's saying is the X-rays are all cut off. This is where X-rays would be, way down here, and there just aren't any. Thank God. I mean, we're just. So Planck was the one who sort of figured out what was wrong with the classical ideas that would predict this, what's called the ultraviolet catastrophe. That is, you go to the ultraviolet, you get tremendous amount of radiation. And even beyond that, beyond the ultraviolet, into the X-rays, into gamma rays, everything should come pouring out of an ordinary fire. Crazy. So it doesn't happen. And so how does he explain that? He explains it by saying that the modes in the box, the vibrations, the dipoles in the box, have what's an energy which is proportional to h times their frequency, so that they're energy levels. This is where the idea of energy levels was first put forward. What he said was that if you have a certain frequency, that the energy of that oscillator is not anything you want, but the energy, the next level up, has an energy proportional to its frequency. So if you have a spectrum of frequencies from low to high, if you have a high frequency here, the next energy level is here. So let's say you double the frequency. And then if I make it, it's 2F. And then if I go to 3 times that frequency, its energy level would be 3 times higher. So it would be the first energy level. So this is Planck's idea. And the box is composed of all these different frequencies, because there's many ways a box can vibrate. So it's made of all of these. So how does it come about that you don't get very high frequencies coming out of this box? Well, then he uses the idea, all right, I'm putting in a certain amount of energy with my temperature. I'm heating the box, and so I put in a temperature. Let's say I put in an energy in a temperature. Recall that the energy in temperature is proportional to this Boltzmann constant times temperature. So suppose I pick a particular temperature, like this. That's some temperature, and represents a certain energy. Now, Planck's argument is that if I put in enough energy and it's more than the energy of this level will take up energy. On the other hand, this oscillator here needs this much energy to get going. I'm only giving it this much. Well, it's close. And as I say, the energy is really kind of a fluctuation. So this one might get a little bit excited. It might pick up some energy. This one is okay. This one is maybe okay, because you see you want to think of KT as kind of a thermal excitation, sort of like light, but it's fuzzy because of the irregular nature of heat. So it's kind of fuzzy, so it could extend up to here. Now this one extends also at this temperature up to about here, but this one is a little bit too far away already. So this one doesn't pick up any energy at all, because it's HF. It's 3F. Its energy level separation is it's too much greater than KT. So that one will not pick up energy, and it won't radiate. So you can see that as the temperature goes up, more and more oscillators can start picking up energy and vibrating and radiate. On the other hand, if you lower the temperature, you prevent this one from picking up. This one doesn't get any energy, and so it stops radiating. This is a phenomenon when sometimes what we do in the lab, I don't know if you do it, you lower the temperature on something and to get some effect. We call that freeze out. That, at least when I was learning nuclear magnetic resonance, we would talk about the fact that if you have an energy levels, if because of the heat motion, particles can occupy both levels. They sort of get jostled into higher levels. If you cool the thing down, the particles tend to settle into the lowest energy level. And so we spoke of the particles freezing out into the lower energy level. So that is the explanation that Planck put forward. He says that the way you can get the fact that you get a phenomenon like this is that, let's say I start with a very high temperature. I'm way up here. I can get very high frequency oscillators to oscillate. As I lower the temperature, that high frequency oscillator freezes out and stops oscillating. As I lower the temperature some more, this guy stops oscillating. And as I lower it more, this stops oscillating. So I see, as I go from this temperature to this, these oscillators in here get frozen out. So that's the argument for quantization. Yes, ma'am. Yeah, the ones that have extreme, they can cause a particle to jump up. And so it's actually a statistical thing. And it turns out that if you look at Planck's formula, it's right up here. You see this EdF over KT? So it dies out exponentially. It never really goes away, but it gets weaker and weaker exponentially. So that it's a very good point you raised, that there is a slight finite probability that even if you have a very low temperature and a very big energy gap, you will have somebody jump up there. But it goes down exponentially with the gap divided by the frequency. So if you look at that number, see it's on the bottom here, E over HF, it kills off pretty much any probability that you'll be up there. Very important idea. This is a statistical thing which comes up all the time. It's the statistical distribution of the probability that a thing will have a certain energy, known as a Boltzmann factor. And this is Maxwell and Boltzmann worked on this. The same Maxwell who did electromagnetism. Anyhow, so the idea is that the big breakthrough here is that up to that point, if you had an oscillator, we could say that it could have any velocity, it could have any amplitude of motion, and if I shook it, it would shake. But now Planck says apparently not. Apparently what's happening is that it's either in one mode with a certain frequency, or it's a second one. And if you don't give it enough energy to get it into that first excited state, it takes up only rarely, as she points out. It will rarely happen, but very rarely, that it will get excited to that next higher state. So that's the origin of the quantum theory. That we're trying to explain why do these modes die off as you lower the temperature. And the explanation is that the thermal energy is not enough to get those higher frequency modes to vibrate and to radiate. So that's the argument that for quantized energy levels. We don't have very much time. So are there any questions about this? I hope it makes some sense. I give you in the notes a pretty horrific analogy with like if you're trying to feed a lot of people, and if you feed everybody the same amount, you'll need an infinite amount of food. If you have like an infinite number of people, and you feed them all the same and they all live, you'll need an infinite amount of food. So the thing is here now, the difference is, suppose that in order to live, you need a certain amount of food depending on how many birthdays you've had, like your frequency of birthdays, or the oftentimes, so that older people need more food. Then if you have and you only have a certain amount of food to give per person, the horrible thing is the older people are going to die off because they don't get enough food. So you won't need an infinite amount of food anymore because the older ones have died off. That's exactly what's happening here. The higher frequency ones died off because they don't have enough energy given to them. And so those freeze out, and you're left with a finite amount of energy in your system. So that's the one way of looking at it. Oh, we'll talk more on Wednesday.